Welcome to today's Explainer. I'm absolutely thrilled you're here because today we are unpacking the very foundation of our physical world. We're looking at the molecular bond behind elements. We're going to explore how these seemingly invisible building blocks of the universe, atoms, form these complex relationships to build literally everything around you. I'm talking about everything from the water you drink to the screen you're looking at right now.
So, to really understand matter, we have to start by asking a pretty fundamental question. Why do atoms combine in the first place? I mean, why not just float around happily on their own? Well, the truth is, most atoms are inherently unstable characters. You can kind of think of them as restless entities on a constant, never-ending quest for fulfillment. They absolutely hate feeling incomplete.
Okay, let's dive into this. What exactly makes an atom feel complete? Well, it all comes down to these magic numbers: 2, 8, 8, and 18. These numbers represent perfectly full electron shells, specifically the K, L, M, and N shells that orbit the atom's center. If an atom doesn't have these exact numbers of electrons in its outermost shell, it is incredibly unstable, and it will do whatever it takes to reach that magic number.
Here's how we're going to break it all down today. First, the quest for stability. Second, sharing is caring with covalent bonds. Third, the big transfer, ionic bonds. Then we'll learn the by-log rule for naming compounds, and finally, we'll look at the actual properties of chemical bonds.
All right, let's jump right into Section 1, the quest for stability, and how these atoms seek out those full shells. Think of atoms as highly emotional little entities that absolutely despise being half full. They just cannot stand the middle ground. To fix this and reach that magical state of stability we talked about, they basically have two strategies to choose from. They can share electrons, think of this like two good buddies pulling their money together to buy something they both want, or they can do a complete transfer, where one atom simply gives its electron away to another atom that desperately needs it.
Let's take a closer look at that first strategy. Section 2. Sharing is caring. Covalent bonds.
This sharing strategy is basically the ultimate form of chemical friendship. Depending on how desperately these atomic friends need electrons, they form different levels of bonds. If they just need to share 2 electrons total, so one from each atom, they form a single bond. If they need to share 4 electrons, that's a double bond. And if they really have to lean on each other and share 6 electrons, they form an incredibly strong triple bond.
And this brilliantly illustrates exactly how this friendship works in practice, starting with hydrogen. A single hydrogen atom has just 1 electron. But remember, its magic number for stability is 2. Wandering around alone, it's highly unstable. Actually, it's super flammable. But when it meets another hydrogen atom, they agree to share their single electrons. Boom! They form a single bond, becoming H2, which is a perfectly stable molecule.
Now, oxygen is a slightly different story. An oxygen atom has 6 electrons in its outer shell, meaning it's exactly 2 electrons short of the magic number 8. So when 2 oxygen atoms meet up, they realize a single bond just isn't going to cut it. They each have to share 2 electrons, sharing a total of 4 to create a sturdy double bond. This gives us O2, the incredibly stable oxygen gas that keeps us alive every single day.
But wait, atoms don't just bond with exact copies of themselves. Look at water, good old H2O. We have 1 oxygen atom needing 2 electrons, and 2 hydrogen atoms that each need 1. The oxygen atom acts as the center, sharing 1 electron with the first hydrogen and another electron with the second hydrogen. Through this shared need, 2 highly reactive gases combine to form a completely stable, non-flammable liquid. I mean, what an incredible transformation!
But what happens when sharing just isn't an option? That brings us to Section 3, the big transfer, also known as ionic bonds.
In this type of bond, we have a complete exchange. Because electrons are negatively charged particles, giving or taking them completely changes the atom's identity. If an atom generously gives away an electron, it loses a negative charge, making it a positively charged ion, known as a cation. On the flip side, if an atom greedily takes an electron, it gains a negative charge, becoming an anion.
Now, what's really interesting about this slide is how flawlessly this pairing works in nature. Sodium has 1 extra electron that it is totally desperate to get rid of. Chlorine, meanwhile, is exactly 1 electron short of a full shell. So sodium gladly throws its extra electron over to chlorine. Sodium becomes a positive cation, chlorine becomes a negative anion, and because opposite charges attract, they lock together instantly. This big transfer creates sodium chloride, which is literally just the everyday table salt sitting in your kitchen.
Okay, so how do we actually name all these creations? Let's move to Section 4, the Bilog naming rule.
From our source material, this is a fantastic, completely no-nonsense way to accurately name chemical compounds, and it breaks down into 3 super simple steps. Step 1. You just write the normal name of the first element. Easy. Step 2. You look at the number of atoms for the second element to determine if you need a prefix like di or tri. Step 3. You drop the ending of the final element and add the suffix "ide." For example, oxygen at the end of a chain becomes oxide. Chlorine becomes chloride.
To accurately put these formulas together, we have to notice how specific elements have inherent charges, or valencies. Hydrogen has a valency of +1, meaning it wants to give an electron. Oxygen is -2, meaning it wants to take 2. Aluminum is +3. And sulfate, which is actually a group of atoms acting as a single unit, has a valency of -2. Honestly, memorizing these inherent charges is the absolute key to chemical mastery.
Because once you know those numbers, it's like a giant puzzle, and you can use a clever little cross-multiplication trick to build any formula. Take aluminum with its +3 charge and sulfate with its -2 charge. You just take the number 3 from aluminum and drop it next to sulfate, and take the number 2 from sulfate and drop it right next to aluminum. Cross-multiply them, and bam, you get Al2SO4 3, the complex formula for aluminum sulfate built in seconds.
Let's see how this all translates into the real world. Section 5. Properties of chemical bonds.
So the crucial point is that the type of bond these atoms form doesn't just stay on a chalkboard. These microscopic bonds dictate the actual physical properties of the matter you interact with every single day. For example, ionic compounds like salt dissolve beautifully in water, but they won't dissolve in kerosene. Covalent compounds like camphor or mothballs do the exact opposite. They refuse to dissolve in water but dissolve easily in oils and kerosene. Why? Because water molecules actually have slight electrical charges. They act like tiny magnets that can rip apart charged ionic bonds, but they can't grab onto the neutral, shared covalent bonds. It really all boils down to this one core principle. Like dissolves in like, and unlike dissolves in unlike. Charged liquids, like water, will dissolve charged ionic compounds. Zero-charge liquids, like kerosene, will happily dissolve zero-charged covalent compounds. It is a perfect logical harmony happening at the microscopic level.
Which brings us to the end of our explainer. We've seen how the frantic quest for stability drives atoms to share and transfer, building the foundation of absolutely everything. But I want to leave you with this. If the sheer scale of these invisible atomic bonds makes up every single cell in your own body, what other microscopic mysteries are dictating the macroscopic world around you? Thank you so much for joining me to explore the molecular bond behind elements, and I hope this sparks a brand new curiosity for the molecular magic happening right under your nose.